Okay, let's take a look at one of these transformed sine waves and identify all of the physical traits that we can from here. Okay, let's start on the outside with this one. So first, notice the floating constant here. Okay, floating meaning it's not attached to anything. That floating constant is our vertical shift. So I'm going to say vertical shift here. Now, understand how this transforms the graph, right? It takes everything, it takes the entire wave, and because it's +1, it's going to move it up. So we're going with a vertical shift up of 1 unit. And when we shift the entire function up, what we're doing is we're taking that midline that runs through the middle of the wave, and we're moving that up. So that's worth noting here. Okay, so let's say moves the midline. Okay, or that equilibrium value that it's sort of that the graph sort of oscillates over. Okay, so normally with a normal sine wave, okay, and we'll look at this in Desmos here in a second, but a normal sine wave has a midline that is the x-axis, right? An untransformed sine wave would look like this. When we use a vertical shift of 1, that midline, that entire graph is moved up. So this entire graph would be moved up. Okay, let's look at the amplitude. So we look at the coefficient of sine itself, and that is -2, but the amplitude is always the absolute value of that. Okay, so the amplitude in this case is 2, which means we're stretching the graph by a factor of 2. Okay, now stretching doesn't change these intercept points. Okay, we can talk a little bit about that. If we were graphing this by hand, we'd have a little bit more to discuss there. But if we're multiplying the outputs by 2, and those outputs were supposed to be zeros down here, okay, multiplying 2 by 0 doesn't change anything. So keep in mind that amplitude is a non-rigid transformation, meaning it is changing the graph itself, right? Okay, so we're looking at the maximum point and the minimum point. Their output's supposed to be 1 and -1. Those are going to be, let's do it this way. Those are going to be multiplied by 2. So now we're looking at maximum and minimum points that are 2 units above, right? So now if we look at just the amplitude and the vertical shift, we've shifted up, and then we've doubled the distance between the midline and the max and the min, okay? Let's not forget about this guy. What does that do? That takes the entire graph and flips it over. So amplitude is always a positive number, but if there's a minus sign in front of it, that reflects the graph. We will never say that the amplitude is negative. If we see that negative sign, we just flip the graph over. Okay, so we're getting pretty crazy here with our graph at this point. But this point, instead of being up here, we're going to reflect it over the midline down to here. And instead of this being 2 units below the midline this way, it's actually going to be 2 units above the midline that way. So this green graph is now the graph that we would be looking at. Okay, let me get rid of this guy. Sorry. Oh dear. Let me get rid of that guy. Let me get rid of this guy. Okay, so now here's our graph right now. Reflected over, stretched by 2, and shifted up. The phase shift, we take the phase shift all at once. Okay, so we take everything that's in here, right? Now, maybe we should talk about the period first. B is a value of 2 here. That's the coefficient of x. So the length of the period, right? Now think about this common sense wise. When we multiply by a number like 2, you would think that we're doubling the size, but because that's happening inside the parentheses, we're not doubling the length of the period. We're cutting it in half, right? So inside transformations do the opposite of what we would expect. And that's shown by this formula, right? So the formula is 2 pi over b. So in this case, it's 2 pi over 2, and 2 pi over 2 is just pi. So what that means is we're not stopping this graph at pi, we're compressing it so that the wave, the entire period of that wave will occur between the first point and pi, Okay, so whereas normally this is 0 and this is 2 pi, pi is right here. So now our graph has to finish by the time we get to this point. Okay, so we'd be looking at a graph that's compressed, right? We're squeezing it in. Now, we have to look at the phase shift as one transformation because, yeah, this does show that it's compressed, but that's not where that graph's going to be located. Okay, so I'm just showing you that just to talk about the actual compression, but the phase shift accounts for the compression and the shifting that occurs with this +2. So for the phase shift, recall that we take C over B. Now, in this case, right, going by what MathXL has said, which is kind of against what I had talked about before, we would say that C is -2 because it's whatever we are subtracting from X. So if the phase shift is C over B, then this would be -2 over 2, which is -1. Now, again, where's this graph moving if this is a plus, right? Remember opposites day? So we're taking this point and we're shifting it 1 unit to the left. Okay, so the phase shift is -1. All right, let's take a look at how this can be shown in Desmos. So here's our sine wave. All right, let's do this in, there's our sine wave. Oops, sorry. I just do this, there's our vertical shift up. Okay, if I do this, we stretch the graph by a factor of 2. If I do this, it reflects the entire graph over. Okay, so see that again. All right, so there's that graph. There's that graph. It reflects it over. Now inside here, when we have 2x plus 2, okay, so now we're going to be off the scale here a little bit because we've moved the point. We've moved to the point that was shifted up 1, right? That was supposed to be the x-axis or the intercept point, and we have it here at -1, 1. Let me put that up there for you to see. Okay. So this point, this -1, 1, that is the new point from where this point shifted, right? We shifted this point up, right? We stretched the graph, which didn't move it. We reflected the graph, which didn't move this anchoring point where the cursor is right here. And then by the phase shift, we saw that the phase shift was -1, so that point moved to here. So you can still see the reflection down. So you see the sine wave going down right off the bat, right? We have that graph going down because of this negative symbol here. We have it stretched by the 2 that we see here. And then the phase shift accounts for that move that took it all the way to the left. Now, since the period we saw had a value of pi, this point over here where the period ends, notice 2.14. Okay, so what is the distance from -1, where this point is, right? On that midline, there's our midline, right? So here's that point, -1, 1, right? Here's the middle of the period. Here's the end of the period, okay? So you can see the reflection over, the stretching, and you can see the distance from -1 to 2.142 would be 3.142. What's 3.142 approximately, right? That's pi, so that's our period length. So identify that midline, the stretch, the reflection, okay, and that phase shift to get an idea about what this graph's going to look like.